Hey y'all, in today's video we're going to be taking a look at the next periodic table trend, chemical reactivity. In general, the reactivity of an element is predicated on its ability to gain or lose electrons. The electrons which are going to be interacting are going to be those which are in the valence shell of these atoms, which is why in the end this is a periodic table trend. It all comes back to Coulomb's law. It all comes back to understanding how elements and their valence electrons are going to be related to each other in terms of force of attraction. There's a large breadth of different types of reactivity. On one side are the extremely reactive elements, but on the other are elements that are essentially non-reactive. We would know those as inert. Inert means relatively non-reactive. Now, almost all elements could be forced to react. However, if we're talking about an inert compound or an inert element, we're talking about an element that is largely unlikely to react. Generally speaking, when we're talking about inert elements, we're mostly talking about those that reside in the eighth group. These are the noble gases, everything from helium down. However, keep in mind that as with everything, you can force a reaction to occur, and some of the elements that are actually further down in those noble gases, xenon and krypton and the like, actually can react and sometimes do. So as I said, the idea of reactivity is tied very closely to Coulomb's law, where it's force of attraction on the valence electrons. You're more likely to lose a valence electron if you're not as attracted to it, and you're less likely to lose a valence electron, and in fact more likely to gain valence electrons if your nucleus is more attracted to them. Now, one thing we learned in the most recent video is that metals tend to lose electrons. This is their metallic character, right? And the metallic character is the likeliness of losing an electron, versus nonmetals are going to gain electrons. Reason is metals have a weaker force of attraction on their valence electrons due to a relatively small effective nuclear charge and generally larger number of shells or energy levels. Nonmetals, meanwhile, are more attracted to the valence electrons because they have a larger effective nuclear charge and fewer energy levels or shells. Remember, it's a combination of both of those variables that lead to one being more likely or less likely to attract its valence electrons. But because of this, we have two different types of reactivity. There's metal reactivity, which is the likelihood of losing an electron, and then there's non-metal reactivity, which is going to be the likelihood of gaining electrons. So in this periodic table trend, there's actually two high points, if you want to think about it this way. The first high point would be that for metals. Metal reactivity is going to be the highest for an element like francium, which has the most number of energy levels and the smallest effective nuclear charge. Meanwhile, for nonmetals, reactivity is going to peak at fluorine, which has the fewest number of energy levels compared to the highest relative effective nuclear charge. Remember, those noble gases are not going to be considered reactive. They are considered inert, so we're actually not going to consider them in these reactivity questions. So with metals, reactivity is based off of a smaller effective nuclear charge and a larger number of energy levels, which is why for metals, it's going to be to the left and lower on the periodic table that you have the highest reactivity. All right. This correlates very well with ionization energy. So ionization energy is lower for those elements, those metals, and that therefore they are going to have a greater metallic character. They're going to have a greater reactivity as metals. For nonmetals, it's going to get higher as you go up and to the right on the periodic table, with the exception of the noble gases. And again, this comes back to Coulomb's law, and it also correlates with electronegativity. The higher the electronegativity, all right, the more reactive those nonmetals are going to be. Oftentimes, we're going to look at this qualitatively, not quantitatively. However, when we get later in the year, we actually are going to be talking a little bit of quantitative components to this. It's going to be called the reduction and oxidation series later in the year. But right now, we're going to look at something called the activity series, the activity series. The more reactive an element is, the higher it is on the activity series, which means we have two, one for metals and one for nonmetals. And in general, we can see these trends play out. However, there are some nuances to it. All right. The most reactive metal on the activity series might not necessarily be the one that you'd predict to be the highest just based off of what you see on the periodic table. So always, always, always use the evidence of an activity series before you're going to use the theory of a periodic table trend. So for instance, if on an activity series you see lithium is at the top, that means that lithium is the most reactive metal on that list. It's the most likely to lose a valence electron. So later in the year, we're going to call this an oxidative process or oxidation series. But right now, we're just knowing it as the metal activity series. Like I said, with lithium at the top, it's the evidence that lithium is the most reactive here. Even if that might not be exactly what you would have predicted on the periodic table, that is what's reality. That is the evidence. So always use the evidence in front of you, but without an activity series, you can generally make these predictions based off of Coulomb's law and your periodic table trends. If we look at the activity series here for nonmetals, again, you're going to see that fluorine is on the top. All right, it's going to gain electrons. It's a nonmetal. It's going to gain electrons. We know this as reduction later in the year, but right now we're just going to talk about this as the evidence. If we have evidence, we can use this to supersede any of our predictions based off of periodic table trends. But without the table, we would be able to use the periodic table trends and Coulomb's law to make a general prediction. There is a quantitative way of measuring your likelihood of gaining or losing electrons, and it's known as E of reduction or E of oxidation. The E of reduction is gaining electrons. And so the E of reduction, the more positive it is, the bigger that number is in the positive direction, the more likely an element is to go through that process to gain those electrons. For an E of oxidation, it's the opposite. The E of oxidation is the likelihood of being oxidized, which is losing electrons. Oxidation is loss of electrons. So when we look at the oxidation process, an E of oxidation is going to tell us the likelihood of it being oxidized. The more positive an E of oxidation is, the more likely it is to be oxidized, which is losing electrons. So metals are going to tend to have more positive E of oxidations. Nonmetals are going to tend to have more positive E of reductions. But as with everything, you need to look at the evidence. The evidence will tell you everything you need to know. And Coulomb's law is a wonderful resource to use in the event you don't have that evidence in front of you. So that wraps up today's video. Today we looked at reactivity as it pertained to metals losing electrons and nonmetals gaining electrons. We talked about reactivity utilizing both the concept of a periodic table trend, but then also the evidence of activity series, and then the kind of the foreshadowing of what we're going to do in the future, which is looking quantitatively at something called the E values, E of oxidation and E of reduction. We're not going to really look at that a lot in this unit. We will look at that back in unit 2 when we get to redox reactions, which is reduction oxidation reactions. And we're going to talk about that a lot when we get to electrochemistry right at the end of the year. Today's video was written, directed, produced, and edited by Jack Schuler and Dawson Rose. Thank you all for watching it. I hope you enjoyed it, and I'll see you in the next one.